On the 9th of November 2007, astronomers pointed a telescope in Hawaii at an object that, just 3 weeks earlier, had been an unremarkable, barely visible comet drifting quietly through the outer solar system. What they measured that night defied belief. The object in front of them now stretched nearly 1.4 million kilometers across, larger than the diameter of Jupiter, larger even than the Sun itself. Picture the comparison image researchers eventually released to make sense of what they were looking at. A small, sharp photograph of Saturn placed beside the comet's own now enormous glowing cloud. The ringed planet reduced to a barely visible speck against the sheer scale of what had, only weeks earlier, been an almost invisible point of light. It hadn't grown a new core. It hadn't collided with anything. Something inside it had simply, suddenly, let go. This is the story of what happens when an object near Earth's orbit swells to a size larger than the largest planet in our solar system. Why? Scientists dropped what they were doing to investigate immediately, and what that investigation revealed about one of the strangest, least predictable events a comet can ever produce. Before going further, it's worth being precise about exactly what actually grew that large, because the distinction matters enormously to understanding the physics involved. The object responsible for this story, a comet called 17P Holmes, did not itself become a solid body larger than Jupiter. Its actual icy nucleus, the compact, solid core at the heart of any comet, measured only a few kilometers across, a modest chunk of ice and rock, unremarkable by any measure, smaller than many mountains here on Earth. What expanded to planet-dwarfing proportions was something else entirely. The coma, the vast, diffuse cloud of gas and dust that surrounds a comet's nucleus once solar heating begins, vaporizing the ices trapped inside it. A coma is, by definition, mostly empty space, an enormous but extremely thin haze of released material, nothing like a solid planet in density or mass, despite briefly rivaling, and in this case exceeding, the physical size of the largest world in our solar system. A genuine case of appearances, telling almost the opposite story from what was physically true. To understand why Comet Holmes's transformation genuinely alarmed and fascinated astronomers in equal measure, you first need to understand how thoroughly ordinary the object had been right up until the moment it wasn't. Discovered back in 1892 by British astronomer Edwin Holmes, observing from London using a comparatively modest telescope by today's standards, the comet had been tracked through the solar system for well over a century, following a predictable, well-mapped orbit that carried it out beyond the asteroid belt and back on a roughly 7-year cycle. Its behavior documented across more than a dozen previous returns without a single comparable incident. By late October of 2007, it was a faint, thoroughly unremarkable object, glowing at around magnitude 17, dim enough that only dedicated amateur astronomers with serious equipment were bothering to track it at all, a footnote in most professional observing schedules rather than any kind of priority target. Then, on October 24th, 2007, everything changed within the span of roughly 24 hours. The comet's brightness surged by a factor of nearly 500,000, rocketing from a barely detectable smudge to a point bright enough to see with the naked eye. An outburst so sudden and so extreme that it remains to this day one of the largest documented brightness increases ever recorded for any comet in the history of astronomy. That initial explosion of brightness was only the opening act. Over the following weeks, as astronomers around the world scrambled to point every available instrument at the suddenly fascinating object, the expanding cloud of gas and dust released by that outburst kept growing, steadily, visibly, night after night. By the time researchers at the University of Hawaii's Institute for Astronomy, using the Canada-France-Hawaii telescope, took the measurements that made headlines that November, the coma had ballooned to roughly 1.4 million kilometers in diameter, larger than Jupiter, and according to the team's own comparison, images released alongside the measurement larger even than the Sun. Pictures released at the time placed the comet's swollen coma directly beside scaled images of Saturn and the Sun for comparison, and in both cases, the tiny distant comet's gas cloud dwarfed the planet and rivaled the star. Scientists moved quickly to investigate exactly what had triggered an eruption of this scale, because nothing about Comet Holmes's prior century of tracked, predictable behavior had hinted that anything like this was coming. The leading explanation researchers converged on involves a sudden, violent release of pressure building up beneath the comet's surface. Comet nuclei are porous, fragile bodies, loosely packed mixtures of ice and dust that formed billions of years ago in the cold outer reaches of the early solar system, held together by little more than their own weak gravity and the occasional patch of more tightly bound material, structures closer in consistency to a dirty, loosely packed snowball than to solid rock. As a comet's orbit carries it closer to the Sun, even briefly, solar heating can penetrate. Beneath the surface, and begin vaporizing pockets of ice trapped within the nucleus, ice that never gets the chance to vent gradually and safely because it's sealed beneath a crust of darker, less volatile material built up over countless previous orbits, a kind of insulating skin formed from dust and organic residue left behind after repeated passes near the sun slowly boiled away the more volatile ices closest to the surface. If enough of that subsurface ice vaporizes and enough pressure builds up without any gradual outlet, the result can be something close to a genuine, if slow-motion, explosion, a sudden rupture of the nucleus's outer crust that releases an enormous quantity of gas and dust all at once. Rather than the gentle, continuous outgassing more typical comets display as they approach the sun, the cosmic equivalent of a shaken bottle finally losing its cap rather than being slowly, carefully opened. Researchers studying Holmes's specific outburst found supporting evidence for exactly that kind of mechanism. Spectroscopic observations, which let astronomers analyze the specific chemical composition of light coming from the expanding coma, revealed the classic signature of fresh, previously unexposed ice suddenly being exposed to sunlight for the first time, material that had almost certainly been sealed beneath the comet's surface for a very long time before erupting all at once, chemically distinct from the more weathered, sun-baked material that made up the comet's outer crust before the rupture occurred. The sheer quantity of material involved was itself staggering. Based on the size and density of the expanding coma, researchers estimated the eruption released hundreds of thousands, potentially even millions, of tons of dust and ice into space, an amount that, spread across a rapidly expanding sphere already dwarfing Jupiter within a matter of weeks, still amounted to an almost unimaginably thin, wispy cloud once you accounted for how much empty volume that material actually had to fill, the astronomical equivalent of releasing a single teaspoon of flour into the volume of an entire football stadium and calling the result a cloud. That density detail is worth sitting with, because it's the key to understanding why an object this physically enormous posed absolutely no danger to anyone, and why astronomers were fascinated rather than alarmed by what they were watching. Despite stretching wider than Jupiter, the total mass involved in Comet Holmes's entire outburst remained a minuscule fraction of the planet's actual mass, spread across a volume so large that the resulting coma was, in practical terms, close to a vacuum, dramatically thinner than the wispiest cloud you'd ever encounter in Earth's own atmosphere. Thinner, even, than the best laboratory vacuums scientists can create here on the ground. A spacecraft could have flown directly through the heart of that expanded coma and barely registered the encounter, its instruments picking up little more than the faintest trace of scattered dust particles. Stark reminder that size and substance are two entirely different measurements when it comes to comets, and that a comet's outward appearance during an outburst like this bears almost no relationship to how much actual material it contains. Astronomers also use the event to study something considerably harder to observe under normal circumstances: the internal structure and history of a comet nucleus, effectively laid bare by its own violent rupture. As the expanding coma continued, growing and thinning throughout November and December of 2007, researchers using the Hubble Space Telescope captured detailed images revealing an unusual asymmetric structure inside the cloud, including what researchers described as a distinct off-center point of brightness near the nucleus, evidence that the eruption hadn't released material perfectly evenly in every direction, but had instead blown out more forcefully along certain paths than others, likely reflecting genuine structural weaknesses or fracture lines within the comet's own fragile, porous body, invisible seams and weak points built up over more than a century of repeated solar heating, finally giving way all at once rather than gradually. Studying exactly how that asymmetric plume evolved over the following weeks, tracking subtle shifts in its shape and brightness night after night, gave scientists a rare, detailed look at the physical process of a comet nucleus fracturing and venting, a process almost impossible to study directly under ordinary circumstances, since it normally happens too gradually or too far from Earth for this level of detail to ever be captured, hidden either by distance or by the sheer slowness of more typical, gradual outgassing that never produces anything dramatic enough to warrant this kind of sustained, detailed observation. Comet Holmes's dramatic transformation also reopened a broader scientific question that astronomers still actively study today: exactly how common and how predictable these kinds of massive outburst events actually are among the broader population of comets passing through the solar system. Most comets brighten and dim in a fairly smooth, predictable way as they approach and recede from the sun, governed by straightforward, well-modeled physics involving how much ice sits exposed on the surface at any given distance, a gradual curve astronomers can chart and forecast with reasonable confidence months or even years in advance. Sudden, dramatic outbursts like the one Holmes experienced remain considerably harder to predict, since they depend on hidden internal structural details of each individual comet's nucleus, weak points and buried ice pockets that simply can't be observed directly from Earth before an eruption actually occurs and reveals them, effectively invisible until the moment they stop being invisible entirely. Researchers have since cataloged other smaller-scale outburst events on a range of different comets, tracking dozens of more modest brightness surges across the years since Holmes's own eruption, but few, if any, have matched the sheer scale of Holmes's transformation from a barely visible speck to an object larger than the Sun in such a short span of time, making it a genuine, still unmatched benchmark case within the field more than a decade and a half later. There's a genuine, ongoing research value in events like this one that extends well beyond a single comet's dramatic month in the spotlight. Every outburst studied in this kind of detail adds real data to models describing what comet nuclei are actually made of and how they're structurally held together, information that matters directly for planetary defense research more broadly. Understanding exactly how a comet's fragile, ice and dust body can suddenly fracture and vent under the right conditions feeds directly into broader efforts to understand how these objects might behave if a mission ever needed to interact with one directly, whether through a sample return effort or, in a more urgent scenario, an attempt to deflect one found to be on a genuinely threatening path toward Earth. A comet nucleus prone to this kind of sudden, unpredictable fracturing behaves very differently under stress than a solid, uniform rocky body would. A distinction that matters enormously for engineers designing any future mission that might need to physically alter a comet's trajectory, since a spacecraft impact or gravity tractor approach calibrated for a solid, predictable body could produce wildly different, harder to forecast results against something as structurally fragile and unevenly built as Holmes's own nucleus turned out to be. It's worth being completely clear for anyone who might come across a title like this one and wonder if it describes an imminent threat about exactly what did and didn't happen here. No solid object anywhere near the size of Jupiter has ever been found near Earth's orbit, and nothing about Comet Holmes's dramatic 2007 outburst represented any kind of danger to Earth or anyone on it. The comet remained roughly 240 million kilometers from Earth throughout the entire event, safely on the far side of the asteroid belt the whole time, and even its enormously expanded coma, despite its record-breaking size, consisted of gas and dust so thin and so diffuse that it posed no physical hazard whatsoever, even to spacecraft that might have passed directly through it. What made the event worth investigating wasn't danger. It was the rare, genuinely spectacular opportunity to watch, in real time, exactly what happens when a comet's hidden internal structure suddenly gives way, transforming an unremarkable, barely visible object into something that, for a few remarkable weeks, physically outsized every planet in the solar system, visible to millions of ordinary people simply looking up at the night sky without any telescope at all. The public reaction to Comet Holmes's outburst was itself part of what made the event scientifically valuable, in an unusual, almost accidental way, because the comet, brightened to naked-eye visibility so suddenly and so dramatically, amateur astronomers and casual skywatchers around the world began photographing and reporting on it within days, generating an enormous informal archive of observations spanning far more locations and far more consistent nightly coverage than any single professional observatory could have managed alone. That crowdsourced record, contributed largely by hobbyists pointing ordinary backyard telescopes and cameras at the night sky, ended up providing researchers with a remarkably detailed night-by-night timeline of exactly how the coma expanded, brightened, and eventually began to fade, filling in observational gaps between the more sporadic, highly scheduled sessions available on major professional instruments like Hubble and the Canada-France-Hawaii telescope. Few astronomical events in the years since have benefited from quite that same scale of combined professional and amateur documentation, a genuine testament to how visible and how genuinely startling the transformation appeared to anyone who simply looked up. So here's where that leaves things. Somewhere out in the solar system right now, other comets are quietly orbiting the Sun, their internal structure just as hidden, just as unpredictable, and just as potentially fragile as Comet Holmes's was right up until the moment in October 2007 when something inside it finally gave way. Astronomers have no reliable way to predict exactly which comet might be next, or exactly when its own hidden fractures might finally rupture under the right combination of solar heating and internal pressure. Think about what that unpredictability actually means for how astronomers approach comet observation more broadly. Every comet currently being tracked, cataloged, and casually monitored by observatories around the world carries at least some small and zero chance of undergoing an outburst somewhat like Holmes's own, a possibility that turns routine, low-priority monitoring into something closer to standing watch, patiently checking in on thousands of faint, distant objects on the outside, chance that any one of them might, without warning, do exactly what Holmes did. That's part of why survey telescopes and automated sky scanning programs have become such a valuable part of modern astronomy. casting a wide enough net across the sky night after night that an unexpected brightness surge on even a previously obscure, rarely observed comet has a real chance of getting caught and studied in detail within hours, rather than being missed entirely until days or weeks later, once the most dramatic, informative early stages of the eruption have already passed. What astronomers do have, thanks to the detailed data gathered during Holmes's own transformation, is a considerably better understanding of what to look for and what questions to ask the next time a faint, unremarkable point of light in the night sky suddenly, without warning, begins growing larger than a planet. The specific spectroscopic signatures, the asymmetric plume structure, the staggering but ultimately harmless density of the expanding cloud, all of it now sits cataloged and cross-referenced, waiting to be compared against whatever the next great cometary outburst eventually reveals. Nobody knows which faint, unremarkable comet will be the next one to do it, or when. But somewhere in an observatory right now, on any given clear night, there's a real chance that astronomers are already watching it happen, one quiet, routine observation at a time, waiting to see if tonight is the night an ordinary point of light decides to become something considerably larger than anyone expected.